So, hello everyone. Can you hear me? Anybody from the
Yes, sir.
students?
Audible.
Yes, sir.
Yes,
Oh,
sir.
Yes, sir.
okay. So I'm Professor Patel. Like I'll be teaching with Professor Burma, Professor Rakesh, and Professor Srinivas. Uh, so today we'll be talking about this UCS test. Okay. So let me share my screen first. Okay. Can you see my screen?
Yes, sir.
Yes. So this is about the UCS test, right? So can you see me and can you see a sample here?
Yes, sir.
So what we do here is we take a sample like this, a cylindrical sample typically, and then what we do is we take this sample to a loading frame where we can put some compressive load to the sample, and we see how it is behaving, like how it is deforming, right? Uh, till it fades, right? So that is this is very simple test, and we have different things here, right? Like this, as I said, this is a loading frame, and then we have a sample here, right? And then we have something called strain gauge. I'll be talking about that later. And and then we have load cells to record our loads, right? And then we get something called a stress strain curve. Okay, again I'm telling you, like I'll be explaining in details about these things. So, and in stress strain curve, we get a plot like this, right? Maybe this is not ideally for rock, this is for steel. So how it works is like it goes all the way up to a peak and then it fades, right? So this is about the test. But the question is why we need this test, right? So anybody from second year can you just tell me like why we need to do this test? Anyone or maybe third year? So third year you had your rock mechanics class, right? Anyone from
Yes, sir.
third year?
So we do this UCS test to find the friction angle and the cohesion of the sample.
No. We don't do the UCS test to get the cohesion and friction. We do the direct shear test or maybe a triaxial test. Okay, so we'll be talking about that later. Like, let's say, I just want to explain this, and I put this example here. Okay, so this is a potash mine in Canada, right? So, and what we are trying to do here is we are trying to get the potash out from the ground, right? And this is kind of a flat deposit. I hope you understand these terms. If you have any questions, just let me know. So this is our ground surface, let's say, okay? And this is the deposit. So what we are trying to do here is we are trying to get this potash out from the ground, right? And so let's say we somehow either a shaft or an incline or ramp, we go inside, right? And try to get all the potash out, right? So what will happen? Like the whole thing will collapse, right? Like everything will go down. So what we usually do is we leave some pillars, right? Leave some pillars so that the roof will be supported and the persons who are working here, they are kind of safe, right? So that is the main target. Like as a mining engineer, we need to take care of that. So these are some examples of the mine pillar. Okay, so this is where the pillar is kind of stable. Okay, so and this is a pillar where it is kind of failed. Okay, so we don't want this, right? We don't want this. And how do we know about this? Is what we do is model the whole thing in a continuum board. Like this board is called flag. Okay, this is flag. So what I'm trying to show here is, or what I'm trying to model here is, let's say this is the whole rock, and in here we have this kind of a potash deposit, right? And in here, what I'm going to do is, I'm trying to take the material out and leave some kind of a pillar here, okay? And I'm taking the material here out and leaving the pillar. So when I'm doing this, what is happening is, let's say this figure here shows how the stress condition, how it is changing inside the material, inside the ground, right? So our the potash maybe deposit was somewhere here, okay, and we are trying to take it out by making some excavation, and we are trying to leave some pillar here, right? So this thing, and you can see like the stress values, how much is coming to this like before the excavation is around 11 MPa here. Okay, and when I take this material out, this blank thing here is when I take this material out and I leave a pillar here, right? And when I excavate this pillar, what is happening? The stress state here is increased, like the vertical stress is increased, and that is, and why is that? Is the load is being transferred from the sides to the pillar, right? So this is in this case it has been increased to 17 or maybe 19 MPa. Okay, so the thing is, like my material here, which is here, should be stable, right? Like when I'm excavating the whole thing. So this need to be stable, and as a mining engineer, I should like I should not leave too much material also to make it like more safe, right? So there should be some kind of a optimization we need to do here. Anybody has any question?
Sir, your voice is not that much clear.
Voice is not clear.
Yes, sir. Yes, sir. Your voice is not coming clearly.
In between
I don't know. Just give me a second. But any question about this? I don't.
I think voice is clear, Professor Patel.
Was it clear?
Yeah, it is clear. I think
Yes, sir. It is clear for me as well.
maybe for a few people.
it's clear for me, sir.
It's echoing.
Okay. Let me see. Yes. Guys, I have no idea. Is it clear now?
Yes,
Or
sir.
is it okay?
Okay, sir.
Not too bad. Okay. So, yeah. So let me share my screen now. Yeah. So what we are doing, like I was just talking about, the first thing is the stability, right? So whether the pillar is stable or not. And the second thing is the displacement. So if you see the previous figure here, let's say this roof here displays too much, then we don't have space for this machine to work, right? So there are two things here. One is this what is whether the pillar is stable or not. Second thing is how much it is displacing, right? So for this, what we need is we need to know the strength of this material here, right? One is the strength. In terms of UCS, we are trying to find it out. We have also different kind of tests. We will be discussing about that in our next labs, right? So, and another thing is the displacement. For the displacement, what we need is our elastic constant, E and nu, right? Right? So, so just to know these three things, one is the strength, second is the Young's modulus and Poisson's ratio. We need to do these kind of tests, right? Like this UCS test. And first thing first is the standard, right? Like we need to follow some kind of standard. Like this is something called International Society of Rock Mechanics, right? ISRM. So this is a body actually who governs like how we should do our test, right? Like so, if you go to their website, you just Google ISRM. So then you can find out like they have their suggested methods, right? And how to do the test. Also, they like there are a few videos that is available there, right? So you can just quickly go through that. And what it says, like this is kind of a reference, right? I'm giving the reference where it has been published, right? So and you can just Google these two reference and see how you need to do the test, right? So to understand that you have to go to these kind of standards. Okay, so just to tell you like what it suggests, there are a few kind of recommendation. I just put some of those here. So first thing it is saying that the straight cylindrical specimen length to diameter ratio of 2.5 to 3. So what we need to do the test is a cylindrical sample, right? So can anybody tell me like can we use other kind of sample, like why not cubical or prismatic?
Sir, the stress may be uniform this way.
No, like even if you take a prismatic sample like this, right? You can do the test, but it's easier to core a sample, like make a cylindrical sample. But to make a prismatic sample, cut a sample in rock is difficult. Okay, so that's why we usually use a cylindrical sample. Okay, and the second thing what it is saying is the ends need to be flat within 0.02 mm. So what it is saying is like let's say this is your top surface, it should be flat, right? There should not be kind of undulating. So third thing is what it is saying is how we should apply the load, right? We should not apply it very fast, or maybe we should not apply it for, let's say, we cannot do the test for, let's say, 5 days, right? We have different kind of test, it's called the creep test, but we are not doing here. So they have suggested some kind of strain rate. What is the strain rate? How fast we are going to load this sample, right? And also like in terms of per second, like the strain per second, or in terms of like this MPa per second. Okay, so it suggests that okay, we need to increase the load gradually between 0.5 to 1 MPa per second. Is this clear to everyone? And there is some scientific basis to this. Yes.
Apart from the easy coring of the cylindrical sample, I think we only get axial stresses only in cylindrical type shapes. Apart from that, we cannot get any shape which will have like axial stresses. So that's why.
You know, like if you see the concrete people, like the civil engineering people, they usually prepare a cubical sample and they do the test, right? So it's the same thing, but in case of rock, like what happens? Let's say this is your ground surface, and your project is somewhere here, your mine is somewhere here, where you want your properties of the rock, right? So what you need to do is first you need to drill a hole here, right? Okay, to get the sample. So you take a drill rig and you take, let's say this is 500 meter deep. Okay, so you have to drill this hole all the way where you are going to make your project, and then you take the core out, right, from there. So it's difficult to make this like get or impossible to get the cubical sample or different kind of sample from here, this depth. Okay, but if you see the concrete people, they use the cubical test, right? Is this clear?
Yes, sir.
Yeah. So because we have different kind of layers here, right? Like we to get the sample where we are doing the designing, before going for the project, we need to take out the core, and that cores, they are kind of cylindrical. I hope it is clear. Okay, so the first thing what we talked about is like the L by D ratio should be 2.52. Sorry, L by D ratio is 2.523, right? And this figure explains here why we need that. So if you have a like a shorter sample with less L by D equal to 0.5. So what is this L? Let's say this is your cylinder, and this is your L. Okay, this is L, and this is your diameter. So if the L by D ratio is too small, what it does is it confines, like because of the friction, it confines the specimen around this area. Okay, and we have a very little space where we have two UCS kind of condition. Okay, so this condition may be a triaxial condition. You will be learning about this, like the second year people, maybe students, you will be learning about this in your rock mechanics class later. So that is why they recommend a longer sample, like the ratio should be greater than 2.5, between 2.5 to 3. Any question, anybody? No, okay. So see, this is again another thing which has been explained here in this figure. So what we did here was, let's say we are plotting the strain rate, right? How fast we are applying the load to the sample. Okay, so in first case, let's say we applied it 1 into 10 to the power 1 into 10 to the power minus 6. Okay, second, the last one is, let's say 1 into 10 to the power 1 into 10 to the power minus 2. So what we are doing here is we are trying to load the sample very quick in here. Okay, so what happens when you do this? You get some additional kind of strength, right? Like, because it's very difficult. It's like a dynamic kind of testing, right? Like if you let's say you have water here, and you try to hit the water with a stick, right? So if you do it very slowly, the stick will go very quickly, right? Like, or it will be easy. But if you just try to hit the water with this stick, it will be very difficult, right? So this is the same thing that's happening. So when you apply a very high strain rate, it's similar to that concept. Okay. So when you apply this high strain rate, it gives you higher strength. Okay, so you can see there is a the difference in strength is 27.2%. Anybody has any question?
So there was a
Yeah.
bending moment in the last PPT. There is a bending part. So if
Yes. So what happens, like why we don't go above 3, right? This L by D equal to L by D. The suggested value is 2.523. So why do we go? We don't go beyond 3, right? What will happen beyond 3? So let's say you have a very just to explain, I made this very long. Okay. So when you load these kind of samples like XCLE, what it does is it try to bend. Okay. So this is not a pure UCS condition now. Okay, this is kind of a like, and it will fail here, like because of the bending. Okay, so that is why there is some kind of limit to what is the maximum value of L by D. Is clear?
yes, sir.
I hope you asked about that thing.
Yes, sir.
Sir,
Sure.
Okay, okay.
can you
So
explain about yes, sir?
you want me to explain again?
No, sir. This 27.2% strength increase. What is that?
Oh, okay. So see, like in this case, what we are doing is we are loading this specimen at a strain rate of 1 into 10 to the power minus 6. What does this mean is, let's say this is your length of the specimen, and we are trying to change the length of the specimen here, right? So what is the, let's say per second, I'm trying to change this length. Okay, this is how I'm loading, and I'm moving the top button towards the sample, right? So let's say this is your del L. Okay, so what is this change in length by length? That is your strain, right? In axial direction. So we are just looking at what is this del L by L per second. So I'm trying to increase that. So initially it was 1 into 10 to the minus 6, and it's going all the way up to 1 into 10 to the minus 2. Okay, so when I'm doing that, the strength, this here is your UCS value. So the first case I got a UCS value of 48.5, right? And when I'm increasing this trend rate, I'm moving it very fast. It is going all the way up to 61.6. Okay, so there is an increase. That is why I said, like guys are they recommend some kind of trend rate. You should not go beyond that. Okay, so you will learn about this again in your rock mechanics class, right? Like in your theory class. Is this clear?
Yes, sir. Yes, sir.
So yeah, so we have our Hooke's law from our school days, right? So stress is directly proportional to strength, and it is related to Young's modulus. So this is what we are trying to find here, right? And this is how the typical stress strain curve in UCS test looks like. So I'm not going to explain in detail, but like there are a few things, right? So this is axial strain. So what is this axial strain? In axial direction, how the sample is changing, right? There is a strain. So and you have your when you compress the sample, let's say your sample is here, and you are compressing the sample, right? So when this length is changing, like this, the corresponding diameter is increasing, right? So in this direction there is a strain. So that strain is your radial strain. Is this clear? What is this radial strain and axial strain? Anybody has any doubt? Okay, and this is your axial stress. What is this axial stress? I am applying a load F, and I'm dividing this with the area of this sample, right? So F by that A is your stress. So what I'm doing, I'm just keep on increasing the stress of the sample, right? By putting some strain. Okay, so this is, yes.
What is radial strain?
What is that?
Radial strain.
Oh, radial strain. So what is happening is the diameter of the sample, when I am loading the sample, right, from the top, the diameter of the sample is changing. Let's say initial diameter was 54 mm, like before loading. Okay, so after loading for, let's say, 20 kilonewton, so when you put a load of 20 kilonewton here, the diameter is increased to, let's say, 54. I'm just giving an example, okay. So 54.1 mm. Okay, so the change in diameter, which is your, what is that, is 0.1 mm, right? Divided by original diameter, so 54. So whatever that value is coming is your radial strain. Is this clear?
Yes, sir.
Okay, so we have here, that's why we have axial strain, which is happening in axial direction, the direction of loading, and we have another strain, like which is happening in radial direction. Okay, so we have different kind of things here, like we are not interested for this lab. Like there is something called crack damage stress, and then crack initiation stress, right? So if you want, you just Google this and try to learn. So, but I just want to tell you something here, like when we load this kind of sample, we have different kind of phases. First is called crack closure phase. Okay, because however intact the rock looks like, there are some voids. Okay, so when you increase this load here, the void gets closed, right? So we have that crack closure phase, and then the rock behaves linearly elastic manner. Okay, so up to something called a crack damage phase. So this is kind of a yield point. From there, it deviates from linearity, and it goes to the peak. Okay, so there are few things like stable track growth and all those things we are not discussing here. If you have any question, you can just call me or send me an email. Is this figure clear to everyone?
Sir,
Yes.
sir, why does changing the rate of applying load affect the strength of the core?
See, like when we try to, like these are made of grains, okay? Like these rock samples are made of mineral grains, you can say. And when you apply this load very slowly, okay, so it becomes easier for it to make the fracture thing. Like this is the failure within the grain. Okay, but if you see, if you apply a like a load which is very fast, the development of the fracture becomes a little bit difficult. As I gave the example of this water, right? Like if you try to hit the water like very fast, right? This is very difficult, right? This behaves like a rigid material, this water. But if you put the water very slowly, it is kind of just a similar kind of concept, right? So if it's very fast, the whole thing, the configuration, whatever there in this rock grain, it doesn't allow the fracture to develop. It is very fast. This is clear?
Yes, sir. Sir, and I had one more question, sir.
Yes.
Sir, for the different lengths of the core, we will get different values of UCS.
Yes.
So, sir, if you are checking for 3:1 ratio in the lab, then
Yes.
we get for that ratio of the sample, like wherever the wherever, like if we leave pillar in a board and pillar mining, then we will leave the pillar in the ratio 3:1. Like we are testing.
Yes.
Okay, sir. Okay,
Yeah,
sir.
no, like we don't have to do like that. Okay, see, this is kind of a the things becomes a little bit complicated there. Okay, so let's say this is your real pillar, and this is let's say 2.5 meter height. Okay, so even if like if you see this looks like a UCS test here, but it's not. Okay, as I said, on top of this thing there will be some kind of confinement, right? Even if you see there will be some kind of confinement inside the pillar. Okay, so this pillar itself behaves very differently. That's why we need those kind of FEM software to know what is the stresses. Okay, so maybe the boundary condition at the boundary, right on the boundary here, we have pure kind of the UCS condition. So what that software does it for us, it divides the whole thing into something called zones. Okay, so I think we are going too much into it, but let me quickly explain. So in each zone, this rock has a different boundary condition. So inside it is kind of a triaxial boundary condition, surface it will be UCS boundary condition, right? So this is kind of a property, whatever the UCS we are getting here, this is a property of a material, right? So when we are modeling that is applied here. It's not like we have to, let's say you have a mine, right? And the thickness of the seam is changing, and here it is, let's say 5 meter, here it is, let's say 3 meter. So you don't have to do a test for 5 meter, LYD equal to 5 meter, and LYD equal to 3 meter. You don't have to do that. Okay, you just get one UCS value and put it in the model. Is this clear?
Okay. Yes, sir. Yes, sir. Got it, sir.
Yeah. So yeah, as I said before, we have kind of this axial strength. I explained about this, right? And we have diametrical strength, the change in diameter by initial diameter. Okay. So then we have this different kind of Young's modulus. First is called tangent Young elastic modulus. Okay. So because this is, as I said, this is a curve, right? Like this is not a straight line. So if you see your still, it goes all the way to yielding point. It's like a like a linear line up to the yielding point for steel. Okay, but raw behaves very differently. You have like oops. So you have this kind of thing, right? So each at different points, the slope of this line is different. Okay. So and the Young's modulus is also different. So tangent modulus is usually we take it typically 50% of the peak. Let's say if you have your rock sample which failed at let's say 50 MPa. So what we do is we get the point where this is 25 MPa and we try to get the slope of this line here. Okay, so let's say this is 1 and this is 30 GPa. So your Young's modulus is 30 GPa. So this is tangent Young's modulus. Anybody has any question about tangent Young's modulus? Okay, so then we have something called average elastic modulus, right? Like, and this average Young's modulus is, let's say, from here to here, this behaves like a elastic material. Okay, so what we do is we join these 2 points, and we get this strain value. What is this del epsilon A, and then we get this. What is this del sigma axial? So that del sigma axial divided by del sigma strain is your average Young's modulus. Anybody has any question? You know, for the design, we don't like, because this Young's modulus is changing. We don't use let's say the Young's modulus from here, right? What we do is we use this average elastic modulus for the straight part. Okay, so this is what we want to find in the laboratory today, right? Like, and there is third type of Young's modulus we calculate is like the second modulus, right? So you take a point anywhere and then you join that point with the origin, and whatever the slope of this line comes, that is your Young's modulus of like the second Young's modulus. So either you can take it to 50%, 100%, right? Like of the peak. This is clear. Like this is what we want to find it out. One is Young's modulus, and anybody has any question? No? Okay.
So what is the meaning of 50% peak strength?
Okay, so see, like what I said is, let's say we are doing some testing of this sample and we are loading the sample, right? So this is stress versus your strain. Okay, and this is how it looks like. And maybe it feels, as I said in the previous cases, let's say this is 50 MPa. Okay, so 50% means what is this 50% of the peak? So that is 25 MPa. Okay,
so
so
25 it will fail.
no, it will not fail. We are trying to, because see, the material behave differently. If you see in our previous, yeah, here. So we have different kind of phase, right? Crack closure phase, elastic region, right? And then stable crack growth, unstable crack growth. So what we want to do is we want to see like that when this is linear, right? When this is linear, what is the slope of this line? What is the Young's modulus of this material? So that gives us Young's modulus, and that is why in that linear part of this curve we try to get the try to get the Young's modulus, right? Because that is the linear part. Does that make sense, or you still have any question? And please feel free to ask. Like you can ask anything.
The Young's modulus is changing at every point because the slope is changing at every point in that first case.
Yes, but you know, once this crack closure phase is done, this is the crack closure phase. So from up to this yielding, where it starts yielding. So from here to here, this is kind of a linear behavior the rock shows. Okay, so if you remember the Hooke's law, stress is directly proportional to your strain, right? And as stress is Young's modulus into strain. This is only valid for the elastic reason, right? So that is why we are more focused at 50% of the peak. If you still have any question, please let me know, like, or maybe drop me an email. I'll reply. Okay, or call me. Okay, so let's go ahead and yeah, next thing is we need to find out Poisson's ratio, right? Like, and what is this Poisson's ratio? Is like your diametrical strain negative of diametrical strain or the radial strain divided by your axial strain. Okay, so this is your Poisson's ratio. This is how it is defined. So what it means is, let's say this is your curve and we are trying to find out the Poisson's ratio here. Okay, this looks like something like this. So this is your axial strain, this is your radial strain. Okay, so let's say at 50%, what is this value divided by what? What is this value here? This, let's say this is x and this is y. So minus of x by y is your Poisson's ratio. Is this clear? I'll show it to you like from our real data. Any question? No. Okay. So now what we need
excuse me, sir.
Yes.
Sir, in the formula, axial strain is on the numerator, and you have written x upon y. Y should be above.
Oh, like see, both are strain values here. What I'm trying to say is this value from this to this distance. So this is your corresponding value of radial strain, right? From here to here. So let's say this is 1 into 10 to the power minus 2. Okay, and let's say this value is let's say 4 into 10 to the power minus 2. And that is, this represents 4 into 10 to the minus 2 represents this distance, right? From origin to this distance. Okay, so and which is your y I'm saying. This is not y-axis, don't get confused with that. Okay, or maybe I can write A and B. Okay, so this is A divided by B. This is clear?
Yes, sir. That is, you have written in term of distance.
Yeah. So this is what is this distance? What is this? Or what is not distance actually? What is this strain and what is this strain? I think it's clear, right? Okay, let's go.
Sir.
Yeah, so first thing is we need to prepare the rock samples, right? And we have to do these kind of things in our, if you remember, in our first class, we talked about coating, cutting, and polishing. We have already shown it to you. If you could not attend the class, you please go through the video and you can see this. Okay, I'm not going to tell about this. So, and the first thing, how do you get it, the core? As I said, let's say we are constructing something 1,000-meter deep. Okay, so maybe any mining or some super secret like this nuclear repository or something. So first thing you need to drill a hole here, right, and to get the core. Okay, so let's say these are those cores. Okay, so sometimes it's possible that because like we don't have access to those holes, and maybe we know that okay, this material will be coming here, right? And similar kind of material, like in the form of boulder, we just take it, right? And what we do is we take it as we have said, like we do the coring thing. Okay, so this is kind of a cylindrical. This is kind of a hollow cylinder. Okay. So this guy, it rotates and rotates, and it kind of cuts this material, and you get something like this one here. So yeah, and we have different kind of that diameter of that coring bit. Okay, and the answer suggests about NX size sample, like it's called NX, and the diameter is 54.7 mm. So what does this mean is you have to take a core whose diameter is 54.7 mm. So this is, there is some scientific basis to this, and we are not going to talk about here. It's related to the maximum grain size and at least few number of grains. I cannot make it like let's say very tiny, right? 2 mm or 3 mm. I cannot do that. That's not. This is no. Okay, so this is what we have to do. Just remember this, and later when we drop in this class, you'll be learning more about this. So then once you get that core, this is called a diamond shaw cutter. Okay, so it this thing rotates, and it cuts the rock sample for us. Okay, and then we do the polishing, right? Like this is called a surface grinder. So this guy here, it rotates very fast, and it polishes the top of this kind of sample. Anybody has any question? No. Okay.
So
And
the
then we check.
polishing is done only on the surface of top surface, no?
Yes, top surface, because we cannot do the
Otherwise,
side
the
polishing,
diameter will
right? Like,
become reduced.
yeah. So yeah, so on the top surface only we do the polishing, and then we check like whether it is flat or not. Like as I was saying, like whether it is wavy or like this is flat. This should be flat within some limit, right? So see, there are a few things we need to see. So this there in that code or maybe standard. So first thing is this line or maybe this plane should be perpendicular to this axis of the loading, right? Otherwise, what will happen? Like when we are loading the sample, so this is your bottom platen, and we are trying to load it. So there will be some kind of stress concentration, and the sample will break somewhere here. Okay, so we don't need that. So this should be perpendicular. Okay, and second thing is this. If this is there is some kind of this kind of material there, right? Like it's not flat. So what will happen? It will get some kind of loading here, where there is like it's just the platen, the top platen will touch the sample first. So there will be, and there can be some local fading. We don't need that. Okay, so that's why we have this kind of like this code, like or the standards is recommend something. Okay, and yeah, then we need some kind of apparatus. Okay, this is our machine, like we call it universal testing machine or UTM. Okay, then we need strain gauge. So what this strain gauge does is like it records the strain for us, and how it works is this is kind of a foil or maybe metal thing. When there is a change in length, so it detects, okay, because it has some kind of resistance. So you know from your +2 physics, like rho R equal to rho L by A, right? So if there is a change in length, it detects this resistance change, this detects this length change, and that is converted to your strain. Okay, so yeah, so this is how it works. Then we need parallel plates. Parallel plates means it is attached here. Okay, so it is not shown, but parallel plates. And then we need some kind of suitable measuring devices also. On top of that, we need something else. We will be discussing that. So this is about the UTM machine, right? Like this is what we have in our lab. It has some capacity of 3,500 kilonewton. So if you want to test like see what is the maximum stress this can apply, you can divide this with the sample diameter, right? And you can find out, like, let's say, what is the maximum stress you can apply to this. So what the maximum load that can be applied is 3,500 kilonewton. And then you have different kind of things here. You can just quickly go, right? I'm just skipping those. And then you need something called data acquisition system. So what it does is these are the strain gauges here. Okay, so this is connected to, if you see here, the sample will be connected to the computer here through some wire and through data acquisition system, so that we can get the strain values in this computer. Okay, so these guys, they do it for us, is called data acquisition system. Okay, so it has some kind of specification. You can just quickly look into that. And once the test is done, we you know, like we get this kind of curves, right? And as I have said before, we get the axial strain, we get the lateral strain or radial strain, right? And the curve looks like this. I think we have the. Can I ask, like, you guys got time to watch the video? Anybody? The one I have shared.
Yes, sir. The video was not having any audio. So that was
Yes, but I wrote the subtitle, right?
yeah, sir. That was subtitle.
Okay. Yeah. So yeah, I will explain that actually. What is happening. So once that is done, like we have this observation kind of table, right? We note down. Let's say we have different samples. Sample 1, 2, 3. We note down our the peak load, right? We divide the peak load with our your area, right? And you get the peak stress, right? And this then you can get the strain values, right? For your Poisson ratio calculation, and then you can get your Young's modulus, right? And then your Poisson ratio. So this is how it works, right? Maybe if you have seen that lab manual, these things are there and it is explained there. Okay, so please go through that. So now the question is, how do we get our UCS, Young's modulus and Poisson ratio, right? So before that, we will watch that video, okay, and I'll try to explain what we are doing here. So yeah, this is about our experiment number 2, and these are the different kind of equipments, the things we need. This is to know the dimensions, right? These are sample, these wires and everything in here. This is here to get put the strain gauges in the sample, right? So and this one here, maybe you can see like whether the connections are good or not. We have this device here, right? And these tiny things here are the strain gauges, the soldering iron, and we have these kind of stuff, right? Like so to put the strain gauges. So see here, what we are doing is we are taking the dimensions of the dimension of the sample. We usually take the dimension at 3 places because you know during pouring is possible that the surface is not that smooth, right? And different locations the diameters are different. Okay, then what we do is we take the length of the sample. We are taking the length of the sample again at 3 different locations with rotating the sample, right? And we note down those kind of things, right? So, and then what we are doing is we are trying to clean the surface here to put the strain gauge. Okay, so because you know, like if you see this is a sandstone sample and if you see the surface, it's not kind of 100% smooth, right? So when you put some kind of glue to put the strain gauge, it will not stick nicely. So we need to prepare the sample. So we are using some sandpaper to polish it so that it will be smooth and that the strain gauge will stick to that. Any question?
Sir, why can't we take the readings after making the sample smooth, sir?
Like see, we have like we are not going to make the samples smooth all around. This is a place where we are putting the strain gauge. Okay, so that is not required actually. Sounds good. you can see this here. So this is the place, only that place. Your question is very much valid, but we just to put the strain gauge, we are polishing it. Okay, like we are using the strain this sandpaper. Yeah, then we are trying to clean the surface, right? And then again is trying to clean it. Yeah, and then finally see this. Oops. This small thing here where the stick mark is, this is our strain gauge. That is what we are going to put it on the surface. Okay, so we are using this sticky tape to take that, because we cannot damage this strain gauge, right? This is very sensitive. So see, this is how he does. He's using this tape. So yeah, tape to get the things right. And then on top of that, what we are doing here is we are putting the glue. It's kind of a super glue, right? So that we are putting on the surface, and what we are doing is along the either like the axial direction or radial direction, we can put this strain gauge. This is kind of clear, because there that was radial, so this one we are putting in axial direction. Yeah, so you have to hold it for about 1 minute so that that thing will stick. So this is we are trying to make a connection, right? We're putting this wire, like there are two ends to this. I mean this strain gauge. So because this is, as I said, that is kind of a resistance, right? That's a resistance. So there are two ends to this resistance. One is connected to this wire, and the other one is this one. So to record, sorry, I mean record the change in length of this and further the resistance of this strain gauge. So yeah, once that is done, we try to fix it, because when you are moving the sample, like it comes out. So this is where we are checking the resistance of the sample, right? So, and yeah, so two ends you have to, because sometimes it happens like that these strain gauges are broken, right? And that's why we check. And then what we do is we place this specimen under that loading frame. And if you can see here, like along with the strain gauges, we have extensometer. So this is kind of a mechanical thing, right? Like when you compress the sample from top, you can see the chain here, right? Like this chain thing here. So there will be a change in length, and like our data acquisition system, it can record the change in length, right? So and you can get the string. Yeah, so these are connected to this big thing here is the data acquisition system, and this is further connected to the computer. Right. So yeah, this is how we are connecting those strain gauges to the data acquisition system. Like we need to see which is our axial strain, which is our radial strain, right? And anybody has any question up to here? Did not understand. So
we are using strain gauges and extensometer both at the same time.
And just to get kind of see this rock, like they are not that very much uniform material. It's not like steel, okay? So what it does is, let's say this is your sample. So we cannot rely on one measuring system, right? Like, so either you put two strain gauges, right? So that if one is broken in between and you will get some data, right? So here we have just shown, actually we have the results of two strain gauges only. We don't have the result of the extensometer. But we just wanted to show you that we have extensometer also, which can be used for your strain measurement. Is it clear?
Yes, sir. Also, sir, can we use a strain gauge once it has already been used? It was not get broken. Then can we use it again?
That not broken. No, no, no. You cannot use that. You know, like see, once that is stuck to that surface, it's very difficult to take it out. I said that's super glue. If you want to take it out, and it will be broken, right?
Sure.
Yes.
Excuse me, sir.
Yes.
Sir, why you have put one gauge in axial direction and one gauge in radial direction?
As I said, like we need to see if you see we need to calculate our Young's modulus, right? Young's modulus is your stress by strain in axial direction. So that is why we need to put one. For example, we need to put one axial strain gauge. Okay. So then I said that Poisson's ratio is negative of your radial strain divided by axial strain, right? So just to calculate what is my Poisson's ratio, I need to put another strain gauge in this direction. So what this first strain gauge will do is that will record how the sample is deforming in this direction. And the second one, what it will do is how the diameter is increasing. This diameter initially, whatever it was there, how it is increasing, that it is recording. Okay, that's why we need at least two strain gauges to get our properties like Young's modulus and Poisson's ratio. Is this clear?
Yes, sir.
Okay. So yeah, so this is how it is connected, right? We can forward a little bit. Yes. So and yeah, you can see like this is the load it is recording, and this is gradually like we are moving this pattern to the specimen, and yeah, so and this is the stress strain curve we are getting, right, for the specimen. So one is for load, like there are two computers, like there are various systems we are using here. So we are getting the different strain values and the load values. You can see here, like, yeah, I think the sample, yeah, see, the sample is broken now. Like, if you keep on increasing that vertical load, at some point of time, it will kind of, like this crack will happen. But after this also, this took some load, right? So initial pressure was there. We will see the stress strain curve for this, and then I'll explain. Okay, and then also it took some load, right? So from its initial fracture, yeah. So we have to load the sample till it's failed, right? Completely, yeah. So this is how it looks like, right? When it is failed completely and it's not taking any load, and this is how the surface looks like. Interesting, right? But no, yeah. So yes, no, okay. Okay, so this is how the things looks like, right? We have three things here. I just wanted to show. First is the radial strain. Okay, that one we are getting it from the sample in radial direction. So in radial direction, how it is, the strain is there, and then we have our axial strain. Okay, so this is here. So we have calculated it in percentage. Why percentage is like this strain values at which this rock fails is very little, right? So how do we calculate that percentage strain is, let's say this is the strain in axial direction, and the sample is kind of change in length is for a particular value, let's say this is del L, and the initial length is L. Okay, so the absolute value of del L by L is your the strain values EA. Okay, so we just multiply this with 100. Okay, so just multiply this with 100, and that becomes our percentage strain. And anybody has any question? So this is how most of the people we can easily, like, we don't multiply with 100 also, and we just keep it like axial strain in mm per mm. So we can keep it like that. Is this clear? Maybe not, right? Anybody has any question?
So the values for the compressive stress should increase, and but in the line of set 10th and 11th row, they are not like that. So.
Yeah, it's in the beginning of the test is like there is some this kind of thing is there. Okay, so once it gets little bit of like, you can say that the sample is trying to settle down. Okay, so before that there is some kind of minor difference. Okay, so once it gets around, let's say 1 MPa or 0.5 MPa, then there is like the continuous increase. Then you cannot get like see that thing. Is this clear?
Yes, sir.
So, but I have modified that data
Excuse me, sir.
because yes.
So earlier you showed a graph in which radial strain is in negative direction, but here axial strain is in negative direction.
No, this is axial. See, this color is axial here, and this is in axial. This axial strain is positive.
Okay, yes, sir, yes.
Okay, this radial is here, and this is negative. Any question? As I have said, like this compressive stress, I have discussed like F by A, right? So you get your load value and then divide it with the area of the specimen, then you can get your compressive stress. Okay. So first thing is, let's say here. Did you understand about this table here? What we are going, because what we are going to share is like these tables, right? With these data. So you have to, maybe you can use Excel and you generate this figure, right? And from there you have to calculate all your values. The UCS is very simple, like whatever the peak value here. So in this case, it's, I think, 28 MPa. 28 MPa. So that is your UCS. So UCS is not that big deal, right? Like, but what I said previously is we need to get the Young's modulus and Poisson's ratio when this line is kind of linear. Okay. So that is our next. Anybody has any question about UCS value? Because this one you have to do it in your kind of report, right? So any question? How do you get this UCS value?
Sir, how shall we calculate the slope?
For slope, you have to use Excel, right? So either you take it to a graph paper or you plot it, right? But in Excel there is options, right? Like you can get the data point here, and you can find what is this value. Like, let's say this value, right? And this value. So the Young's modulus, for example, I'll show it in the next slide. Let me go there. Okay. So first thing, what you can do is you can plot these values based on the data which we are going to provide you. Okay. So it will be like that. And first thing, UCS. UCS is very simple, right? As I said, just what is the peak of this thing is your UCS. For us, it's around 28 MPa. Now, how I do is, let's say I take this linear part, okay, because this is where the material behaves elastically, right? And what I can do is I can get this data point, right? Like you can, from your Excel, you can get these values. Okay, so if you see, this is, let's say, 21.5. Okay, and this value, let's say, if you just draw a line, let's say this is 6.8. Okay, so what is this distance? This is, or maybe change in stress, del sigma A, you can say, is 21.5 minus this 6.8, right? Is this clear? The change in this,
Yes,
this is del sigma A. Okay, and what is this? This is your del sigma, epsilon A, right? Change in your strain, right? Like this value. So this is, let's say, this is 0.3, and this is 0.12. Okay, so what is the del E strain? Axial strain is your 0.3 minus 0.12, right? And your Young's modulus for this material will be equal to your like your this value divided by this value, right? So 21.5 minus 6.8 divided by 0.3 minus 0.12. Anybody has any question? So, but you know, there is some issue with the unit here. We need to see that, right? So what? See this
Hello.
top part, yeah.
Sir, to calculate the tangential strength, you told that we have to consider 50%. Can you explain that part?
Yeah, so what you can do is like you take this, this is 28 for us, right? Okay, so you have to find the point here where it is 14. And you have to draw a line. Okay, so this is the point. So this is the point where you need to find the slope of this line. So that is the tangential Young's modulus at 50%. Okay.
Sir, how shall we have to find derivative?
Not derivative. See, this is what I'm trying to explain. If you see, let's say, what is the strain value corresponding to this stress value? Yeah, you can get the equation of the torque and get the derivative also if you want. Okay. Or maybe there is some option like this is, see, this is the equation of the line. I'm putting it here, y equal to 82.112x minus something, right? So this is where there is something called trend line. So what I did here was, I'm sorry, what I did here was I took some data point from here to here in this range. Okay, took this data point and plotted it again on top of this. And there is something called trend line. Add a trend line. So those guys who don't know about Excel much, you can just Google this. Okay, so you'll find a YouTube video to do that. Okay, so add a trend line. So trend line will be there, and there is some option to show what is the slope of this trend line. Okay, so this is what I am showing here in this video also. So see, I put some, like to calculate the tangential Young's modulus, I put some data point and added a trend line here, and this is the slope of that line. Okay, so slope is 82.112, which is same if you calculate it like this. So this is one way you can calculate, and this is another way. Is this clear to everyone? Else I can explain once more.
So, sir, we are calculating the UCS at approximately 50% of the peak value, no?
No. UCS is on confined compressive strength. Okay, so that is the strength at which it fails. So this is the UCS.
Peak strength.
Okay, the Young's modulus we are trying to calculate at 50%. If you want to calculate the tangential Young's modulus, or you can take the, as I said, you can take the linear portion of this line, right, and you can see what is the slope of that line. That is your Young's modulus for the material in this range. Okay. Yeah, because this is what you are going to do, right? So please, if you have any question, please ask.
Sir, curve is a straight line, so slope will be same in both cases.
Yeah, it should be. Actually, you know, if you take the tangent, it's exactly like it looks like a straight line, but it's not a straight line, even if in this part. Okay. So, if it is 100% straight line, that will be same. You are right. Okay. So, if you see the like this rock behaves very different. Okay. And yeah, any other question? So this is what I am trying to do here. So this is, let's say this is MPa. Why this is percentage of strain? Okay, so percentage of strain. So this one I need to divide with 100. So to get the actual strain, right? Not in percentage. Because to get percentage of strain, I multiplied 100, so I need to divide with 100 to get this strain values. Okay, so this Young's modulus is now MPa. So if I divide the whole thing in this value, whatever it is coming here, with 1000, that will be your GPA. It's in GPA. Okay, so if you see, this is divided by 1000. If this 100 will come to the top, and it will be like whatever this value you get it here. Finally, that value divided by 100 is your Young's modulus in GPA. Is this clear, or is it was? Okay, this is what we want. We want the Young's modulus we represent it in GPA. Okay, so gigapascal. Anybody has any question? No. Okay, so we are almost done here. Please let me. Okay, so this is what I said. The slope of this line is 82. So if you can plot that trend line, your Young's modulus is 82 divided by 10 or 82.1 something. So divided by 10 is your 8.21 GPA. So this is the Young's modulus of this. Is this clear?
But sir, this is the tangent modulus, right?
Yes. Yeah, the tangent modulus, or as you can see, you can check, like in your report you can see like the linear part, if the Young's modulus is different, or then this value, so you can do those kind of stuffs, right? But what we want in your report is in the linear part of this line, what is the Young's modulus here. So this is what we follow when we are going for a design. Okay, right?
Sir, do we also need to find like other like average elastic modulus and secant elastic modulus?
Yeah, you can, if you can put that, that would be great, and you can maybe get some good like more marks in your report, right? But this is must, right? The Young's modulus and Poisson's ratio. So then I will explain you how to get to your Poisson's ratio.
But sir, how is this different from the average elastic modulus? Because there also we are finding the slope in the linear region, right?
If you can see here, right, it looks like linear, but you know, like it is trying to deviate. Like this is not 100% linear. You can try that, okay? Then you just go to Excel and see that, and then we can discuss. Or maybe you can put it in here as a comment or in your report. That okay, like there is a little bit of difference, or there is no difference between this tangent modulus. See, this is not steel, okay? This rock behaves a little bit differently. It looks like linear, but it's not 100% linear. Is this clear? Yeah, that is why we have the different kind of definition. Otherwise, we can say that Young's modulus of the material is at tangent modulus at 50%. right? This is how we define, but it depends upon, like this is what we used in the real design case. Okay. Now, but the question is, okay, for me, it will look like linear up to here, but somebody will be looking like linear up to here, right? So there will be difference. Yeah, of course, there can be some difference. Okay, so in tangent modulus at 50% also you need to get this the slope of this line here, right? So how far I'm keeping it here and here, it depends again. So there will be a small difference. So if the Young's modulus for this case is 8.21 GPa, so if I consider up to here, it can be 8.2 GPa, but I don't care that much. Okay. Is this clear? Like this Young's modulus part? We will go to Poisson's ratio now. And anybody has any question?
Yes, sir. Clear.
Okay. Okay. So the next thing is your Poisson's ratio. How do you get it? So you know, like as I said, this is your del epsilon A, right? And this is your del sigma A. And if you similarly, if you try to get the corresponding value here, so this will be your del epsilon R, and this is your del epsilon del sigma A. Okay, so for us, Poisson's ratio is negative of E R by E A. Okay, so if I just divide this with your del sigma A, so or maybe in terms of del, you can write it like this, right? So del epsilon R divided by del sigma A. I just divide by this del sigma A in top and bottom, right? In numerator and denominator. So this divided by del sigma A. Okay. Or what I can write is del sigma A by del epsilon A divided by del sigma A divided by del epsilon R. Any question? So, but this one, you see, this is the slope of this line here. And this one here is the slope of this line here, right? So if I know my slope in here and slope in here, I can find my Poisson's ratio. That is easier. Otherwise, you know, there is some non-linear part of this, and you cannot take the absolute value of your this axial strain and radial strain. Okay, this is valid only for the linear material like steel, right? Or if the rock is behaving linear, then you can use it. But if there is some kind of non-linearity in the initial part, you cannot use it. So this is what we do. Okay, so this is slope of this axial slope, you can say, or maybe yeah, forgetting the negative thing. So slope of this radial. Okay, so for this, let's say the slope is 82.1 divided by minus of 213.27. Okay, so whatever this is, let's say it is coming 0.29 or something. So that is your Poisson's ratio. Anybody has any question? No?
So, sir, for a last question, sir, if we are providing the values to the Excel, MS Excel part, so will it give us the value?
You know, it's very difficult to hear. Can you please repeat?
Am I audible?
A little bit. Can you speak a little bit loud?
So I was asking that if we can provide the values to the MS Excel part, do we get the values of that slopes and the that extra parts?
Still, I'm not sure what you are asking, but yeah, you can take it to Excel. Okay. So then again, as I said, you can add some trend line. Okay, and get the slope of the trend line from here to here, trend line from here to here, slope of that, and you can just divide those slope of those lines, right? This is y equal to mx plus c. So this is the slope of the line which we want, right? So one side is EA and this is your ER. Okay, just get those two values of A and ER. Anybody who can understand sorry, what's your name?
I was sure with the ninth part.
Okay, so anybody who can understand, like, because it's difficult for me to hear what he's saying.
Yes, sir, I understood that part.
Oh, okay. So you can do that in Excel, or you can plot it, like draw a line here, do whatever you can, right, like, and get the value. Is this clear?
Yes, sir. Thank you.
Okay.
Sir,
Thank you so much. Yes, please.
sir, the plot will be given or we have to plot it?
No, you have to plot it. So what you are going to get is these values. So there will be 3 sets of data, and we will give this column, and this column. And also maybe not this column. I need to see. Okay, so maybe this will be post, and we will give you the raw data so that you can calculate what is your stress, right? And you can calculate what is your strain. So there will be 3 columns. Okay, and you need to calculate corresponding value of strain and corresponding value of stresses. Okay. So axial stress and axial strain and radial strain will give, and you have to calculate this thing. At least you need to do. So so how it will look like is, yeah. So what we are going to do is we are going to give you, let's say, L1, L2, L3, right? And you have to calculate the average value. You have to calculate your diameter D1, D2, D3. Okay, you have to calculate what is the average value. So then you can calculate what is your area. Area equal to pi d square by 4, right? So if I'm giving your F value, like which is continuously increasing, you can calculate what is the corresponding value of your stress, right? So F divided by your area will be your sigma XL. This is clear? And then you have to calculate all the values for 3 samples. Sample number 1 is a sample 1, 2, and 3. Okay.
So do we need to show the plot also?
Yes, of course. You need to show the plot for 3 samples.
We can do that in Excel. I mean.
Yes, you can do that in Excel.
Okay.
Yeah, there will be a lot of data, right? It's let's say you are using graph paper and you are plotting those n number of data. That's kind of a impossible task to do. Maybe it will take a lot of time. So we are not going to do that. What we are going to do is we are going to provide all the data like as I have said, and you just plot it in Excel. Okay, and get the values. Sounds good?
So can you explain the Poisson ratio calculation one?
See, this Poisson's ratio is, let's say we have a linear material here. Okay, so from origin to all the way to yield point, it is kind of linear. Okay, in that case, what we can do, we can divide this value and this value and get my Poisson's ratio. Okay, so for our case, see, this is not linear. This is, the slope is somewhere going like this. The slope is going like this here, right? So the line, I mean, the tangent is going like this. So it's not linear, right? So for that, what we can do is, as we said, like this is also defined as del epsilon r by del epsilon a. Okay, so what is the change in this value? I mean, the change in this value here divided by the change in this value here, that is your Poisson's ratio. Okay, so it is like we are just trying to bring this point here, and trying to get what is the Young's modulus. Okay, so make sense? And so that, yes.
It with change stress then.
Sorry.
Like we have also incorporated the stress factor, right? Delta sigma A. So why are we
Yeah,
doing that?
so you don't have to do that. If you can find this value, right? If you can get this value, you don't need to do that. Okay, if you can directly get it, that's okay. Right, but what I was saying is you can get a trend line, right? So like with the trend line, you can get the slope directly, so you don't have to get it. So if you know the slope, how can you get the value of Poisson's ratio? So this is what I was trying to explain. So no, you don't have to divide this with del sigma A. Okay, if you can get this value directly, you can get the value of Poisson's ratio. You don't have to do it. You are correct. Okay, so either you can do it like this, get the Poisson's ratio by getting the slope of these lines, or maybe you can just get the value of what is this value, what is this value for the corresponding value of this. So, and you get this Poisson's ratio. So either way you can do it.
Okay, so
Any question? Any other question?
So can you explain what we have to do in Excel once again?
Oh, okay. Or can I show you? Okay. So let me share my screen. Can you see my screen now?
Yes, sir.
So what I did here was like this. This is the thing you are going to get. Okay, radial strain, axial strain, compressive stress. So and then you need to plot it. And anybody who doesn't know how to plot this thing in Excel? Okay, so I will quickly tell. Okay, how do you plot it? Let's say start from 0. So
We can see that from YouTube. I mean, there are many lectures for that.
yes, you can see that in YouTube. Okay, thank you so much. So yeah, so this plot here, the right side one is axial stress versus axial strain, right? And this left one is radial strain versus axial stress. Okay, so this is the first thing you need to do. Or I can say that there is some insert, then insert graph, right? And this thing is there. You can click this, select data. So you just please see this. Okay, you should, like being an engineer, you should able to know like how you need to do. Okay, so for that, let's say what I've done here. First, I plotted this one and this thing, right? Like the axial versus axial stress versus axial strain and radial stress versus radial strain. Okay, these two things. Second thing, let's say I want to know my tangent Young's modulus at 50% of peak, right? So what I did was, like I tried to find out the value where it is, the axial stress value is around, because the peak is, let's see the peak. Okay, so just a second. This axial stress value is increasing, right? The compressive stress. And
So you have crossed the peak.
No,
That was
yeah, cross
28.
the peak, but I just want to put a formula here. So if you put this equal to maximum of these two all the way up to 1, or maybe 11. Okay, so all the way up to top, what is the maximum value we can get it? So this is the maximum value of 28.3. Okay, so this is your UCS value, which I was saying is around 28, right? So first thing what we need to do is we need to get what is 14.15. Yeah, because you know, like this system we have in our lab is so powerful. Like we can record n number of data, lakhs of data within the test, right? So yes. So, but what we need to find is 14 point. See, you can see here. This is changing. So we have to find that 14.15. Okay, 14. Very good. 14.15. So we have these two values, right? So what I can do is I can just select some of the values here. Okay. So this is the data point near that 50% of peak. So I'll just copy it. Okay. So and let's say put it here. So and here what I can do, I can put another set of data. This is what I have done here. Okay, if you go to select data, then this thing. So if you see, so I have selected some kind of data here, right? Like, or maybe what you can do, either you select another set of data, plot it here, get the slope of that line, right? Let's check out. Let's say I plot the data here. Okay, so I can right click it, and what I can do, I can add a trend line instead. Okay, so right click and add trend line. So then what kind of trend line you want to add, either linear, exponential. So we need linear because we want the slope of the line, and we just click here, display equation on chart. Okay, so you just click this one, so that this the slope will be here. See the slope of that line, which is at the 50% of peak, is 82.112. Anybody has any question about this? No,
Sir,
right?
this equation is the equation of a straight line, whole straight line, or the trend line?
Yeah, equation of the whole, like, see, you have so many data points here, right? Okay, so you can make it like if the UCS is 28, you can make that get the data point from, let's say, 13.5 to all the way to 14.5. So you can get two data points here. What is the corresponding value of strain here, right? And you can draw that line. Okay, so it is kind of an average value of that data points. So what is the slope? Is it clear or no? Okay, let me explain. Okay, so can you see my screen? Hello?
No, sir.
No?
I don't think it is being shared.
Okay, just a second. Yeah, so can you see it now?
Yes, sir. Visible.
Yes. So yeah, so what happens is sorry. Yes. So let's say these are the data points, right? These cross are the data points. This is what we are going to put. So if you see, they are not in one line. Okay, so this add trend line, what it does is it tries to put the best fit line among these data points. Okay, which is passing through. If you remember, like in your statistics, there is something called R square value, right? So please see that. So like with the minimum R square value, so put this line such that your R square is the maximum, right? So the deviation from this line is minimum. Okay. So this is the slope of this line, not any two data points, right? The average slope of the line which joins these data points. Is this clear? I hope so.
Yes, sir.
Okay, guys, let's stop it here. I think we are done. And if you still have any question, please email me or maybe.
So the graph is make in Excel, right?
Yes, and you can copy and paste it.
Okay, sir.
So what I can do is I can, I can copy that graph or the figure, stress strain figure, and then I can put it in Word, right? And scan it. So do whatever you want, like you can use Excel, right?
Sir,
Yes.
can we use some other softwares apart from Excel, like Desmos app or
Whatever, yes, please, or MATLAB or whatever you want to please use it. Okay, so it's not like you have to use Excel.
So, sir, for this experiment, we can make the observation table in Excel only because the data points are going to be like lot more. So, making it on an Excel will be more feasible.
You don't have to put the data point in your report because it will be thousands of data and it will take a lot of time, right? Like to put it.
Yes,
So
like
please don't put the data.
calculations like for finding strain and.
Yes, so those things you can put it there.
Okay, sir.
Okay, so don't put the data like it will be too much. You just put the figure.
So,
okay.
do we have to write the procedure and the theory part for this assignment also? Experiment?
Yes, it's the same. Like the rule of the game is same for all the experiments. Okay.
Okay, sir.
So no word thing, like no copy paste. You have to write it and you have to do it. Okay, that's the rule of the game.
Okay.
Sounds good?
Okay,
Yes.
Patel.
Yes, please go ahead.